Here in this question, we see that there is a metallic shell, and inside the metallic shell there is a hollow region, and at the center there is plus 3 nanocoulomb charge placed. Now you have to find out the amount of charge that's at the inner ring, that's in this region, and within the shell, that's like in this region, and the outer ring, which is like in this region, right? And now, since plus 3 coulomb charge is placed on the center of the geometry, and since it's a metallic shell, therefore it will attract negative uh, minus 3 coulomb charges on the inner surface, right? So on the inner surface, it's gonna be minus 3 negative coulomb. Inside the shell, the electric field is 0, and there will be no net charges. So inside the charges will be 0 coulomb. And on the outer shell, initially you see the shell was charged with minus 8 nanocoulomb, and this will be distributed on the outer shell. So in the outer shell, you started with minus 8 nanocoulomb, but since because of this positive charge, there is an induced negative charge on the inner shell of minus 3 nanocoulomb. Therefore, this will also induce a positive 3 nanocoulomb charges on the surface. So therefore, on the outer surface, we will have a net of minus 5 nanocoulomb. So therefore, our option will be option number 2. And here we see an electron is moving opposite to the direction of the electric field. So therefore, the electric field direction shown here is going from positive to negative, and it's moving uphill towards the positive terminal, right? So if we have a positive charge, it moves along the electric field lines, right? So therefore, the potential reduces and the potential energy also reduces. But since the electric field moves upwards, therefore it's moving towards the higher potential side, which is defined by the positive charges as it flows from higher potential to lower potential. So since the negative charge move upwards, it's moving towards the higher potential side. And also since it's moving away from the negative terminal, the potential energy also reduces. So therefore, in this case, the right option would be reducing potential energy and increasing the potential, electrostatic potential. Therefore, option number C is the correct option. Now here we see that a capacitor with a capacitance C, but a dielectric material was inserted with in 1/3 of the space, right? So therefore we can assume the initial capacitance C, right? We can assume the initial capacitance C without the dielectric, right? For example, I can consider this one without the dielectric. Now I can consider this to be made up of 3 capacitors, right? 1, 2, and 3 capacitors, let's say. So this is one capacitor, this is another capacitor, and this is another capacitor. Now these capacitors are connected in parallel, right? So therefore, the individual capacitances are 1 by C, right? The individual capacitors are basically 1 by 3 C's, because the original capacitance has to sum up to give you C. And since they're in parallel, the capacitance will sum up, right? Now, you have placed dielectric in one of the portions, so therefore the new capacitance will be 1 by 3 C, which is for the left one, plus K times 1 by 3 C, so that's like 4 by 3C, that's for the middle one, right? The middle one. And for the right hand capacitor, it's also 1 by 3C. So when you sum them up, you will get a new capacitance of 2C. So therefore, option number 4 is the correct option. Now here we see two sheets of positively charged plates, right? Uh, which we know that will induce an electric field in the upward direction with a magnitude of sigma by 2 epsilon naught, right? And also in the downward direction with the same magnitude, right? Sigma by 2 epsilon naught. Now, since these both the plates have the same amount of charge density, so therefore for the bottom plate also there will be an equal amount of electric field going upwards, which is sigma by 2 epsilon naught, and going downward as sigma by 2 epsilon naught. Right now, if we consider the sheet of charges only, you see the upward electric field and the downward electric field at the center, which is at the point A, should cancel out. So there, the contribution of the sheet of charges should be equal to 0, right? But you have an additional plus 2 coulomb of charges, right? Now, what's the distance between this charge and the center point A? Since the separation is d, so therefore the a is halfway towards d, so it's d by 2 plus this distance d, right? So the separation is basically 3d by 2, right? So now what's the electric field formula for point charges? Since this is a point charge, the electric field formula for a point charge would be from the Coulomb's law, right? So that's basically 1 by 4 pi epsilon naught charge, which is 2q in this case, divided by r squared. Right now, r in this case is 3d by 2. So it's 3d by 2 whole squared, right? So which is basically 1 by 4 pi epsilon naught 8q by 9d squared. Now this is for the coulombic charge, right? And the contribution of the sheet of charges is 0. So therefore, the net electric field would be just because of this 2 coulomb charge. So the correct option is option number 3. Now, here the geometries of the two conducting cylindrical capacitor is given, and you have just asked to find out or write the correct expression for the capacitance of a cylindrical two conductor cylindrical capacitor, right? And be aware that these are long. This capital N basically means long. So this is basically a typo error. Don't confuse this with the length. All right. This length. Don't confuse with this length. All right. Now we know from the theory that the formula for the capacitor of a cylindrical capacitor is directly proportional to the length. The capacitor is directly proportional to the length, and it's connected by the radius through the ln function. So therefore option number 3 is the correct option. Now here you see that we have two current carrying conductors with both the currents are coming out of the page, as you can see from here by the dots, right? Now you have to find out the magnitude of one current at the origin is 1 I ampere, and for the other is 4I, right? And they will induce a magnetic field by grip law. If you apply the right hand grip rule, then basically if you point the thumb towards the direction of the current, then you'll have the direction of the magnetic field because of this current flowing to be like this, right? So you see that at some point this upward magnetic field and this downward magnetic field will cancel out, right? So that's the point that they are asking you to find out, the point at which the magnetic field is 0. Because definitely you see that the current in this wire is higher, so therefore definitely this will have a higher strength of magnetic field. Therefore the point of 0 magnetic field will be away from the 4I. It will be closer to somewhere towards the current carrying conductor carrying the current I, right? And it cannot be in this region, because in this region both the magnetic fields are in the same direction, so they'll be adding up. It cannot be in this region also, because here also both the magnetic fields are adding up, right? The directions, only in between they are going, one going up, the other going down. Now if I take a distance x from the origin, right? If I take the point distance to be x away from the origin, then I know that for a current I flowing in the wire, the magnetic field is given by mu naught I by 2 pi r, right? So if I consider for the origin, right, if I consider from the origin a distance x, so therefore I'm considering the magnetic field for the current I to be mu naught I 2 pi x, right? And for the 4I, the distance is d minus x, right? Now this has to be equal, for to cancel out, right? So it's 2 pi d minus x. All right. So now when I simplify, I get basically an equation like this, right? So therefore my x is just basically d by 5, right? And what's my d? D is 5 centimeters. So my x is 1 centimeter. So I will get a zero magnetic field 1 centimeter away from the origin, which is in the positive x-axis direction, right? And also it has to be in the on the positive x-axis direction. So that means my y has to be 0, right? So therefore my option number 2 is the correct option. Now for this one, I have two current carrying wires. I1 is coming out of the page, I2 is going into the page, right? So therefore for this one, if I apply the right hand grip rule, thumb pointing to the direction of the current, I will see that my fingers point to the direction of the magnetic field, which is like this, right? And similarly for I2, my magnetic field is in this direction, right? So now you have to find out the magnetic field at the expression of the magnetic field at the origin, right? So therefore you see for I1, if you proceed for I1, the magnetic field lines, right? It's going to be like this, right? So therefore at origin, you see the magnetic field direction is going upwards, right? Because of I1, right? Now similarly for I2, if I draw, the magnetic field direction is going to the left, you see, going to the left, right, for I2. So therefore for I1 it's going upwards, right, which is positive y-axis or positive j, right, because of I1, right? This is because of I1. And to the right hand direction, which is in the positive x-axis direction or positive I, right, because of I2. So therefore I have to look for I2 expression with I vector and I1 expression with j vector both in the positive. So you see, if I look into my options, I find that my option number 5 is the correct option. Now here we see a metallic wire of radius r, which carries a uniform current I out of the page. Now you have to find out the magnetic field equation for radius is smaller than the radius of the entire radius of the wire. Now we know that for current carrying wire, current for a wire carrying current I with the expression for the magnetic field is this one, right? But in this case, let's say you are looking for a portion of the wire, not the entire one, but a portion with radius r, right? Now remember, the total current flowing in this wire with radius capital R is I, right? So what's my current density? Let's say if I term my current density as CD, So therefore my current density has to be current divided by the area, which is pi r squared, right? Now, if I want to find out the magnetic field because of this smaller region of the wire, right? Now this should also have a similar current density, right? This should also have the similar current density. So this should have, let's say, I, this current I don't know, by pi small capital R squared, right? So therefore, what's the relation between my small I and the capital I? So therefore, the relation is just basically, so what's my smaller I? My smaller I is just basically pi r squared divided by pi capital R squared times I, right? Which is basically uh, r squared times capital R squared I, right? Which makes sense because if you have a smaller radius, you will have a smaller portion of the entire current, right? And since this is a two-dimensional, you have to connect through area. That's why you get a squared portion, right? Now you just have to plug this value into your original equation. So therefore, what's my magnetic field equation for a portion of the current encompassed by an area with radius smaller r? It's uh, mu naught by 2 pi mu naught by 2 pi smaller r, right, times the current, right? What's my current? It's r squared by capital R squared times I, right? So therefore I will get basically mu naught r times 2 pi r squared I, right? So if we look into our options, we see option number 2 is the correct option. Now here we see a magnetic field defined by this sinusoidal function, right, in Tesla, and you have an area given by 1 centimeter by 1 centimeter. That means uh, it's basically, you have to convert that into meter, right? Now, so when you do that, you'll end up getting 0.01 times 0.01, right? All right. Now you have to find out what is the magnetic flux going through this area, right? So we know that our magnetic flux is given by B times A, right? So what's our A? Our A is basically 0.01 times 0.01, which is basically 1 times 10 power minus 4 meters square, right? So that's our A. What's our B? B is given here. So basically, what's our phi B? Phi B is just 10 power minus 4, which is the area, right? Times the B, which is 1 by 200 pi sine 2 pi t, this much Weber. So once you plug in the values, you should get something like 5 by pi 10 power minus 7 sine 2 pi t. Now you see, you don't have this option in the given values, but the closest one is this one, right? Option number 1. But this is just differed by a factor of 100. So I guess this is a typo error because they assumed 1 centimeter. They maybe forgot to assume into meter. That's why the power is changed. Is different, but the option number 1 seems to be the correct option, and in the exam you can ask the invigilators if you come up with an answer which is not present in the options, and if you feel that maybe the options given there is a typo error, so you definitely go and ask the invigilators in the exam. But option, in this case I would say option number 1 is the correct option. Now here we see that a wire is carrying current 2I, and there is a loop of radius r, and now you have to find out the magnetic field at point P. Now the contribution is only from this arc at point P. The straight wire portions does not have any contributions, right? So, and we know that the magnetic field is given for this arc is given by mu naught I by 4 pi r theta, right? In this case, you see theta is, in this case, theta is pi by 2, right? 90 degrees. And what's my radius? Radius is equal to r, and my I is basically 2I. So once you plug in the values, you should get mu naught I by 4 r, right? Also in this case, you see there is a typo error. I guess the correct option is not given here, but that should be the value that we'll be getting. Now we move to question number 3. So basically from here the circuit part starts, and here you see a circuit is given and you are asked to find out basically the Thevenin equivalent of circuit A, right? So you have to assume the top circuit, right? You can ignore everything from the bottom. Now you have, since you are looking for a Thevenin, you are looking to find out the voltage across the load, right? So you are looking to find out the voltage across the load, which is this one, right? And the resistance, equivalent resistances across it. Now, if I consider an equivalent circuit, let's say, I just redraw this one, just for clarity's sake. I just considering that circuit A only, right? Now you see, since I'm looking to find out this Thevenin voltage, right? So the voltage drop across, and this is open circuit, so the voltage drop across this 2 kilo ohms is 0 volts, no current is flowing, right? But for that, to find VThevenin, I have to find out basically, I have to find out the voltage across the source, right? Voltage across the source and across this 1 kilo ohms. All right. So basically, I have to find out the, let's say, I have to find out this Vs and this V1, let's say. Right, so then I have to apply KVL. So if I apply KVL, I will get basically VThevenin plus Vs plus V1 should be equal to 0. So from there I can find out my VThevenin once I know the source, the voltage across the current source and the voltage across the 1 kilo ohms resistance, right? So now to proceed, I could apply mesh analysis, right? I can apply mesh analysis to proceed. Now I can assume now this this so if you see this portion only, right, this portion of the circuit only, you see my 1 ampere, right, my this 2 milliampere, it will be flowing only in this region, right, because there is a short circuit, right, you see, because this is a short circuit, so my 2 milliamperes will be flowing only through this 2 kilo ohms resistance, right. So I can immediately find my VAS. So my VAS by KVL should be equivalent to the voltage across these 2 kilo ohms, right. So what's my VAS? Basically voltage across the current source. It's basically 2 milliamps times 2 kilo ohms, right? So that's like 4 volts. So I know my Vs. Now I have to find just V1, right? So if I'm just looking for V1, and since this is short circuited, so I can assume that I can assume this, I can exclude this part for my analysis. So now I'll have just two loops. I'll apply mesh analysis. I'll consider this to be I1 and this to be I2. So then I'll just write my mesh equations. So for loop 1, I'm assuming my I1 is greater than I2. Uh, so therefore my loop 1 equations will be basically this one, right? So when I'll simplify, I'll get this basically. Okay, this is for the other one. I'll get 6K1 minus 4KI2 equal to minus 10. So this is what I'll get, right? Now for loop 2, I'm assuming I2 is greater than I1. So therefore my mesh equation will be this one. So now when I'll simplify, I'll get 4KI1 plus 7KI2 is equal to 6. So now for two loops, I have two equations, two variables, I1 and I2. Once I solve it, I'll get I1 to be minus 1.77 milliamps. So that means the actual current I1 is flowing like this, right? And my I2 is also minus 0.154 milliamps. So that means my I2 is also flowing like this, right? So therefore, what's my V1? What's my V1? My V1 is just basically I2, right? Or so it's in this case it's just minus I2, right? So in this case, my V1 would be just I2 times 1K, right? Assuming that the current is flowing, I2 is flowing like this, right? So then now I have my V1, right? I have Vs. So once I plug that in to my original equation, remember this one, I should get my VThevenin, right? So therefore my VThevenin should be minus Vs minus V1, right? So which is equal to minus 4.154 volts, right? So this is the Thevenin voltage, right, across the RL. Now what's my Thevenin resistance? Now you see for my Thevenin resistance, I turn off all the independent sources, right? So that means current source is turned off, open circuit, right? So therefore I can ignore this whole junction. This is open circuit, right? No current is flowing here. and I'll short circuit the voltage sources, right? I'll short circuit the voltage sources. So now you see this these 2 kilo ohms, right? These 2 kilo ohms and these 4 kilo ohms are parallel, because you see, if I call this node A, this is also node A. If I call this node B, this is also node B. So these 2 kilo ohms and these 4 kilo ohms are parallel, right? Which is in series with these 2 kilo ohms, right? And this thing is parallel with this 1 kilo ohms, right? And this thing is in series with the other 2 kilo ohms, right? So once you plug in all the values, uh, I'll just show a simplification. So I'll just basically show a simplification just to help you guys visualize what's going on. So this is 2K, this is 2K, this is my 1 kilo ohms, right? And this is 1.33 kilo ohms, right? Which is basically the parallel resistance of 2 kilo ohms and 4 kilo ohms is 1.33 kilo ohms, right? This is in series with these 2 kilo ohms as shown. This is in parallel, this entire thing is in parallel with 1 kilo ohms, right? And this thing is also then ultimately series with these 2 kilo ohms, right? So once you plug in the values, you find your RThevenin to be 4.77 kilo ohms. So that's your RThevenin, right? And also VThevenin, it's minus 4.154. Remember the terminal polarities that you assumed, right? For this one, it's minus 4.154, so we can switch the terminals to get positive 4.154. All right, so this is for part A. Now for part B, right? So for part B, you are asked to find the Thevenin equivalent of circuit B, right? So for the bottom circuit, so you assume everything from the bottom circuit and you ignore everything on the top. Now if you assume everything from the bottom circuit, you see, if I keep my RL to be open, right? So this is very easy. So this is 2K, right? And this is minus plus Vx. 5 milliamps, 1 kilo ohms, right? And this one is a voltage dependent voltage source, 3Vx, right? So that's my circuit. Now you see, what's my Vx? Now this 5 milliampere is flowing only through these 1 kilo ohms and 2 kilo ohms, right? No current is going here, right? Current going here is 0 ampere because the connection is not complete. So what's my Vx? My Vx is just basically 2 kilo ohms times 5 milliamps, right? Which is just equal to 10 volts. Now if that is my 10 volts, what is this 3Vx? This is 30, right? So now what's my Thevenin voltage, right? Because I have to find out the Thevenin voltage. So that's my 30 volts, right? So that's like my 30 volts, right? And what's the voltage across this 1K? It's 5 milliampere times 1 kilo ohms, 5 volt, right? Now look at the polarity, right? Look at the polarity. Now, in this case also, I will, let's say, I assume this to be my Thevenin polarity, right? So if I apply a KVL across this loop, right? So I get minus VThevenin, right? Minus 30 volts plus 5 equal to 0. So what's my VThevenin? It's minus 25 volts, right? For this polarity, remember the polarity. For this polarity, it's minus 25 volts, right? So if I assume the polarity to be like this, then I can say my VThevenin is plus 25 volts. All right. Okay, now I have to find out my RThevenin. remember. Now for my RThevenin, I turn off my sources, right? I turn off my sources, the independent sources. So if I turn off my independent sources, I end up having a circuit like this. So the independent source I have is the only current source, so it will be an open circuit, right? So therefore, right now I have a dependent source. So ideally I would connect here 1 volt or 1 milliampere, right? And then find out my RThevenin. But since Vx is this one, right? So what's my Vx? Vx is 0 volts because no current is flowing. So my dependent source has 0 volts. So that means this is a short circuit. So what's my RThevenin basically? My RThevenin is just 1 kilo ohms. Right? So that's your basically values that you will be looking for, right? Now, in the next part, they have asked you to find RL such that you have maximum power transfer from both the circuit A and B. That's from the top and the bottom, right? Now, this is the circuit that we got earlier. The Thevenin circuit is shown here. So I have adjusted the polarity of the sources to ignore the negative voltages, right? Now, if I plug in RL, what's going to be my RL for maximum power transfer, right? So now here also you see you have to find out another Thevenin circuit in this case also. All right. So for this case, I have to assume I have to open the RL and I have to find out the Thevenin voltage, this voltage across the RL, right? And its corresponding resistance, R Thevenin. So now if I want to find out this Thevenin voltage, you see the two voltage sources are in series, right? And they are opposing each other, right? So therefore I can find out the current has to be flowing in this direction, right? Because my bottom voltage source has a higher potential than the top one, right? So the current has to be flowing in this direction. So what's going to be my I? My I is going to be just 25 minus 4.154 divided by the total resistance, which is 4.77k plus 1k, since this is a series circuit. So my I is 3.613 milliamps, right? So now I have to find out the voltage across this 4.77k kilo ohms resistance, right? So I can term this as V1, right? So what's gonna be my V1 is just 4.77k times this 3.613 milliamps, right? Now, if I apply KVL across this one, so I can find out my VThevenin, right? So my VThevenin will be basically just 4.154 plus V1, right? Equal to 0. So my VThevenin, so once I plug in the values, right? Once I plug in the values, I find my VThevenin to be minus 21.39 volt, which basically means the actual polarity is plus minus like this, right? So I assumed, I assumed this to be different, opposite. So therefore, since I get a minus voltage, I know that, okay, my voltage polarity is actually like this one. For this, actually, the VThevenin is positive 21.39 volts. All right. Now, what's gonna be my RThevenin, right? So for my RThevenin, I assume I turn off all my independent sources as there are no dependent sources. So I just have only two voltage sources here, so which will be short circuited, right? So what's gonna be my RL, RThevenin, right? So this is just 4.77k and this is 1k. So you see, I just have my RThevenin to be 4.77k parallel with 1k, right? So my RThevenin is basically 0.83 kilo ohms, So what's my Thevenin circuit? Since I'm assuming positive Thevenin voltage, so I reverse my polarity. So that's 21.39, right? If you put positive terminal up, so you can put minus 21.39, and this is 0.83 kilo ohms. So that's my ultimate Thevenin circuit that I'm looking for. So what's gonna be my determined RL for maximum power transfer? So definitely, you know, for maximum power transfer, your RL has to be equal to R Thevenin or R Norton, right? So in this case, it has to be 0.83 kilo ohms, such that you have maximum power transfer to this RL, which is basically 50% of the total power supplied by the source. Now here we see a transient circuit. Here we see that at time 0, the switch was switched from position A to B. So basically at t less than 0, the switch was at position A. At t is equal to 0, the switch flipped to position B, right? So I have to find out the voltage function for t greater than 0, right? Which is the voltage across the capacitor, right? So therefore for t less than 0, that means from infinity to 0, I assume my capacitor was fully charged, so it was open circuit, right? So since this was open circuit, the current through this 1 ohm and this 6 ohm is 0, right? So therefore, what's gonna be my voltage drop across the 1 ohms? It's 0 volt. Across the 6 ohms is 0 volt. So what's gonna be my VC? VC is gonna be just voltage across these 4 ohms, right? Which is basically 4 volts, right? So my VC, I can call this, or I can call this VI, right? The initial voltage to be 4 volts, right? So then what's gonna be my VF? VF will be like when you turn the switch to position B, so that's like from 0 to infinity, what's happening. So you see when the switch turns to position B, right? When the switch turns to position B, my capacitor, you see, it will have another voltage, right? It will not be discharging right now, but it will have a different voltage, right? So now when the capacitor is connected to position B, right? And you are moving to time infinity, so you know that is gonna be open circuit again. So therefore the current through this 5 ohm is 0 amps. So the voltage drop across 5 ohms is 0 volt. Similarly, the current through this 8 ohms is 0 amps. Voltage drop across 8 ohms is 0 volt. So therefore your VC will be just basically the voltage across this source. So therefore what's your VF? VF is 10 volt, right? So then you have to find out the tau, right? The time constant, since this is a capacitor, your tau is given by RC, and this R is basically R Thevenin across the capacitor, right? For which time? For t greater than 0, right? T greater than equal to 0. So for t greater than equal to 0, your switch is placed at position B, right? So now for that one, what you do is that you turn off the independent sources, right? And if there was a dependent source, you have to plug in 1 volt or 1 ampere to find out the Thevenin equivalent or the Norton equivalent. Since in this case is just an independent voltage source, so I will replace this by a short circuit, right? So basically what's going to be my R Thevenin? My R Thevenin is going to be just basically 5 ohms. This will be a short because my voltage source is turned off. 8 ohms, right? Now you see, I don't have contribution for these 3 ohms because this is short circuit, right? So this portion is cancelled out. So basically what's my R Thevenin is just 13 ohms. Since my 5 ohms and my 8 ohms are in series, so R Thevenin is 13 ohms, right? So now what's gonna be my tau? My tau is 13 times 0.2, right? So that's like 2.6 seconds. That's my tau. The unit of tau is in seconds, right? So now what's gonna be my VCT? VCT is VF, right? Plus VI minus VF e power minus t by tau. So that's like 10 plus 10 minus 4 e power minus t by 2.6, right? So that's 10 plus 6 e power minus t by 2.6, right? That's my VCT. In part B, so I'll just write VCT here. 10 minus 6 e power minus t by 2.6. So now in part B, they asked you to find derive the function vt for t greater than 0, right? So there are many ways you can do. You can find out the current, you can go to find vt, but you can also apply KVL, right? So I don't know why they gave you 4 marks, but like, I mean, since you want to use the answer from the previous section, which is this VCT, so if you apply KVL, so you'll get minus VCT, right, plus VT plus 10 volt equal to 0. So what's your V? V is gonna be just VC minus 10, right? So your VT is just gonna be VCT, which is 10 minus 6 e power t by 2.6 minus 10, right? So that's gonna be your that's gonna be your VT, right? So which is basically is equal to minus 6 e power minus t by 2.6 volt. All right. Now we end up to the last question, which is a complex number question, right? So you see that you have an inductor given of 5 Henries, capacitor given of 1 microfarad, right? The resistances are given, and you have 2 independent sources, no dependent source. One is a voltage source and one is a current source. Now, what's omega? You see, omega is 200, right? All right. Now, remember in phasor, once you try to solve for complex number systems, right, you have to consider everything in the cosine format. So therefore, this current source is already in the cosine format. That's fine. But your voltage source is in the sine format, right? So the phasor domain for this one would be a voltage shift, right? A shift of 90 degrees, right? So I'll just write the phasor format, right? So this Vs is basically 10 minus 90 degrees, right? And this Is is gonna be just 5 milliamps. That's it, right? Now, in part A, you are asked to find out the DC voltage source contribution to V naught T, right? So you see, once you have this you want to find out the DC volt contribution, right? So that means you cannot compute DC and AC at the same time. So that means you have to turn off the basically you have to turn off the AC sources, right? The current and the voltage source. So once you turn off, the voltage source will be short circuited and the current source will be open circuited. So then you will have basically this circuit. Why? Because in DC, inductor acts as a short circuit, right? So therefore, I'll have a short inductor and capacitor acts as an open circuit. So I'll just open the capacitor. So I have to turn off the AC sources. Also, I have to consider short circuit for the inductor, open circuit for the capacitor. So then if I assume this to be my V naught T polarity, right? Voltage polarity. So you see by KVL, I get a voltage polarity of this to be 10 volts. So what's my V naught T DC contribution? Is just minus 10 volt. And it's fixed with time, right? All right. In part B, I have to calculate the impedances, right? So by impedances, they mean the reactances, which is ZL is equal to J omega L, right? So that's like J times 200 times 5, which is J1K, right? And ZC is basically 1 by J omega C, right? So which is basically minus J 1 by 200 times 1 microfarad, which is basically minus 5 kJ, right? So these are the impedances that you have to find. Now, in the last part, you are asked to find out the AC source contribution, right? So now, since you want to find out the AC source contribution, you have a DC voltage source, right? So you have to turn off this DC voltage source. So that means this will be a short circuit, right? So you see, this is the circuit that you have to consider. So this is just gone. So this is just a short circuit, right? So this entire thing is just one node. You see, this entire thing is just one node. All right. Now I'll just replace these by all the phasor values, right? As I did before, just for simplification. So these are the time values. Just do 10 angle minus 90 because this was sine, right? This is 5 milliamps. This one is J1K, and this one is minus J5K. All right. Now I have to find out the V naught T, right? So now what I could do is like I can apply a nodal analysis, right? Because I can find out just this nodal voltage, right? I can find out just this nodal voltage, which I can term as V1. And once I do that, I have one node, so my V1 should be equal to my V naught T, right? All right. Now, how to find out the nodal voltage? I considered current going out from all the branches, right? So it's like one current, two current, three current, four current, right? So let's write the nodal equations, right? So it's V1 minus 10 angle minus 90 divided by J1K, then minus 5 milliamps, right? Plus V1 by minus J5K plus V1 by 2K should be equal to 0. Now, once I simplify, I'll get something like 8V1 plus 5J V1 equal to minus 50J, right? So what's my V1? Minus 50J divided by 8 plus 5J. Plug this into your calculator. You'll find out your voltage to be 5.3 angle minus 122 degrees. Right, and what's the polarity? This is the polarity, right? So I get my V1, right? So now my V1 should be equal to my V naught, right? But so my V naught should also be like 5.3 volts, angle minus 122 degrees. But that's like in the phasor domain. So what's in the time domain? V naught T. Since I assumed everything in the cosine format, that's why I changed my sine to cosine, right? So my ultimate form would be the amplitude cosine, and what's my omega? It's 200, 200t. What's my phi? It's minus 122 degrees. So that's my V naught t in volts.